the action potential firing to stop here?
Yes.
Probably depolarization block.
Oh, it still is depolarization block?
There aren't any other active currents to stop it.
Okay.
I mean, there's no calcium-dependent potassium current. There's no pump current. There's nothing else that could really be doing it.
Because when you were up at 16, it looked like it would go the entire time and there was no depolarization block.
Yeah, that's a good point. That's a good point. I don't know.
Something weird going on this.
I don't know. Let me think for a moment. How about this? How about there's a trace amount of T current that's available, and even that small trace amount goes away? That seems like about right. There aren't any other currents in the model. So the only thing it could be is depolarization block or inactivation of the T current. And even though the T current is minuscule, it could be that it contributes a little bit in the beginning.
Okay.
All right, so let's go back and just do this one more time with a -1 pulse. We de-inactivate the T current a little bit, so we get a little bit of lump. That's the beginning of a low threshold spike. If I make this a little bit less, we get nothing. And then if I go back to 1, 1, get a little bit of a low threshold spike. And then if I make it 2, we definitely get a low threshold spike, but just with 1 sodium spike on top. And if I make it -3, now we're really seeing the full low threshold calcium spike. We could adjust the duration with T on and T off, and we can adjust the amplitude. And notice my applied current or my bias is 0. There's no bias here. And if I make the amplitude very positive, I can get tonic spiking. So that simulates the first 3 or 4 slides of today's presentation. Now shall we go to parameter set 2? The model looks basically the same, except I should have theta H, KH, and phi different. My current balance equations look the same. The only differences are going to be theta H. See, notice I annotated this. This is something you can and should do for your final exam. If you have good models, annotate them. P1 uses -83.5, but I have it set for 72, which is parameter set 2. KH is 1.1, parameter set 1 uses 6.3. Phi, set at 1, parameter set 1 uses 3. So I've annotated my model to know what's the difference between the 2 parameter sets. And I have the same expression for applied current, but I'm not going to use the steps. I'm just not going to use them. And now I've set my applied current equal to 0 here, but if you now look at the I've set my IO to -1.1. This is mimicking the removal, the disfacilitation of serotonin during sleep. And there's the system giving us low threshold spiking. Notice my right axis I applied goes from -10 to 150, and my red line represents -1.1, my bias current. And then my voltage solutions on the right-hand side are repetitive bursting. So if I went to 0, applied current, should just go back to rest. It does. And now if I added an amplitude of 15, say during then I get tonic spiking. So this is just like what we saw in that movie, where when the bias current is low, the system is giving us spike bursts, and then when the applied current is brought to 0 or pulsed a little bit above, you get tonic spiking. So I'll take the tonic the pulse off and bring it back to minus 1.1. Let's take a look at one of these bursts. I'll vamp a little bit, 400 to 700 maybe. And then I want to show you the clincher. So there's your low threshold spike bursts. Now let's go back to the lecture for a moment. Do you remember in this video when the system was transitioning in and out of its bursting regime? There were these brief moments when you were getting the full burst, but then as you started to depolarize a little bit, you got this smaller burst, and then when you're coming back down, you get a smaller burst before you get the full bursts. There seems to be this intermediate burst when you're between the full bursts and the tonic mode. There are these sort of half bursts in the middle. Can you see that? So I'll show you what that looks like in the model, unless something goes dramatically wrong. So let's go back out. There's our full spike bursts. And now if I make this 1.0 half bursts, because the T current isn't completely de-inactivated, therefore it's not completely available upon activation. I don't know if this is going to work at 0.9. It might just be tonic, or it might just be silent. Yeah, it's just silent. There you go.
And you said that happens because of remnant T current?
It's not fully de-inactivating. So this happens when the applied current is all the way negative, we get the full low threshold spike bursts. But when the applied current is being brought back up a little bit, like we don't have as much, we have a little bit less bias. So the T current cannot completely de-inactivate in the interval between bursts. It can't completely de-inactivate, so it can't completely activate either. It's like an intermediate phase. And the model will do it. There it is. So if you compare this simulation, I don't know, let's just do a batch run. Let's go 3 runs on I/O. We'll start at 0.9 and go to 1.1. Run it 3 times. So you can see 3 different runs there. The blue one is the intermediate value where the low threshold spike isn't even kind of going up high enough to evoke the sodium action potential. Pretty cool, right? Yeah. Okay, that's it for my material. I'll take a question. We have about 5 minutes left.
Any way to accelerate the bursting? Can you get a higher kind of hertz, I guess, or is it just is it always going to be kind of on the same interval?
The frequency of the bursting is largely determined by the activation and inactivation properties of the T current. So there isn't a lot you can do with the frequency. In fact, when this bursting was first discovered, they called it 6 hertz oscillation. 6 hertz oscillation. Let's see, does that hold up? Let's see if that holds up. Go I applied minus 1.1, run it. I'm applying 1 second. 1, 2, 3, 4, 5, 6. 6 hertz bursting. So this was literally described as 6 hertz bursting. And so regardless of what your bias current is, if you can get this bursting, it's going to be 6 hertz. Remember what hertz is? 1 over a second. Not 1 over 1 millisecond, 1 over 1 second. All right, if there's no further questions, you can have the rest of the afternoon. And if I don't see you tomorrow, have a good holiday. Thank you.